Hello everyone, I think we'll get underway with the webinar now. I'd like to welcome everybody to today's webinar. My name is Will Gates, I'm CIRIA's event manager and I'll be facilitating the webinar today. Just a few operational things before we get going. If you have any questions that you'd like to ask any of the presenters throughout today's presentations, you can write your question at any point using the question box. If you could please remember to say who your question is for, and we'll go through all the questions that we have at the end of the presentations today. So today's webinar is another chance to find out a bit more about CIRIA C761, tower crane and tie design in case you missed the event a bit earlier in the year. And we have 3 presentations for you today from Tim Watson, Stuart Marchand and James McFarlane. So without any further ado, I'm going to hand over to Tim, who will get us underway with the first presentation. Tim, are you there?
Yes, I am. Thank you. Okay. Right. Good afternoon, everybody. What I'm going to do is to talk about the document in general, and then Stuart is going to talk about the example calculations in some detail, and then James is going to talk about some particular issues that he has come across in his time with foundation and tie design. Right, the main changes from the previous version of this document is the removal of the operational guidance, which is already contained in Lola and the BS7121 series. This was because we wanted to concentrate very much on foundation and tie design and not fill the document up with operational guidance, which you can find easily from other sources. We've also added catastrophic events in construction to the document, and I'll say a little bit more about that later on. There is a new section on managing the design, construction and maintenance of foundation and ties, because obviously it's no good designing something very well and then not actually building it and putting it into practice in an effective way. We have a new section on foundation and tie inspections, so that after the foundation and ties have been put in and during their life, they are inspected at appropriate intervals to make sure that they are still sound. The section on foundation with worked examples using the limit state approach as in the Eurocodes is one of the main drivers for the change in this document, the revision of the document, because the previous version did not take account of Eurocodes, and that has obviously been a major change in the approach to calculation since the publication of the first document. We have a new annex on loads on tower cranes, taking account of the changes to the calculation of foundation and tie loads, which the manufacturers have adopted, and we include the use of a UK specific out of service wind region map. And then fairly obviously the revision has a new title and a new number. So the actual contents of the document briefly are an introduction, a section on design, the next section on managing the whole process, and then finally a section on foundation and tie inspections. We then have some annexes, appendices. The first one is on different tower crane types and their features. We have then a section on loading and structural elements. Then the real meat of the document is Appendix 3 on foundations, including design examples, and Stuart will be talking about those after I finished my section of this. Then we have foundation construction issues, things to be aware of, and the last appendix is a combined foundation design and completion certificate, which is just an example of a way of dealing with this. We also have case studies throughout the document. We have references, statutes, and a fairly comprehensive further reading list. Now, introduction to the document talks about the causes of failure and particularly the consequences of failure. Tower cranes mercifully don't fail very often, but when they do, they generally have the potential to injure large numbers of people just by the fact that they're very often erected on congested sites in city centres. And we then look at the particular hazards that are associated with the failure of tower cranes. The first one is erection, climbing, or dismantling. The reason that there's a particular hazard is that all of these activities rely on skill and competence. And if the people who are carrying them out are not competent, then there is the chance that it will go wrong. Overloads shouldn't happen on tower cranes because of the systems, load control systems that are built in, but if the cranes are not used properly, then there is always a chance of overload and a failure due to that. High wind loads is a fairly obvious one. If the correct wind region is not selected, then there is always a chance that the winds will be higher than designed for, and that will lead to failure either of the tower crane structure or its supporting structures. Structural failure, you can end up with structural failure of either the crane or the base, very often due to fatigue, which should always be spotted by appropriate inspections and thorough examinations, but doesn't always happen. The other problem you can get is the failure of the load. The load may disintegrate in the air, or it may be dropped from the crane, and that will obviously have an effect on people nearby, or it may actually put some very severe shock loading into the crane structure. Proximity hazards. Cranes need to be protected from vehicles. There have been cases in the past where cranes that have been erected alongside a road have actually been demolished by cars running into them and so on. And then the last hazard we have is overhead power lines, which fairly obviously, if you get the crane too near an overhead power line, or you get the load suspended from the crane too near a power line, then you will get arcing across, and then there is a risk of electric shock danger to the operator and people in the vicinity. We set out the particular health and safety legislation that applies in the UK, particularly to tower cranes, and we also talk about standards and the guidance that's available. And then we talk about catastrophic events in construction. These are events where there is the potential to injure or kill large numbers of people, and we talk about the various factors to consider. And here is a list of the factors that will tend towards a catastrophic event and the factors that will tend away from a catastrophic event, particularly talking about tower cranes. And then moving on to chapter 2, we talk about the loads applied to the foundations, loading information from manufacturers, how to obtain information where the crane manufacturer is no longer in existence, which for old cranes is often quite a problem. We talk about the partial factors that are used in calculations. We talk about the regulations and standards, the influence of siting on design. I'll say a bit more about that in a moment. Foundations themselves, different types, the importance of lightning protection, because obviously a tower crane is very often the highest structure in a particular area. We talk about tying, guying, and then you might wonder why design includes erection, climbing and dismantling, and that is really the design of the foundations for the mobile crane that is used to erect or dismantle the crane. These are often 500-ton cranes, which are extremely large and have high outrigger loads, so therefore the design needs to take account of the foundations for these mobiles. Here we give some little sketches showing the way that the loads are applied to the foundations for both cast-in anchors and also ballasted cruciforms. And these are some examples in the document of the different types of foundations. We've got the cast-in type, where you cast sacrificial anchors into a concrete base. You can bolt the crane to a steel grillage. You can have an unballasted cruciform, where all the uplift is taken by fasteners into a properly designed foundation. And then we have the ballasted type, where you rely on ballast on the cruciform to take the moment out, the overturning moment out of the system. You can mount on rails, and you can also mount statically. And these are the main types of foundations that you'll come across with tower cranes. The other important thing is the influence of siting on design. It's the effect that the crane may have on adjacent structures, or it's the effect that adjacent structures may have on the crane stability. So some examples there. And moving on to chapter 3, we're talking here about managing the design, construction and maintenance of the whole process. So we talk about managing the planning, the design, the procurement, foundation construction, erection, operation, reconfiguration. That's when the crane needs to be changed. You might change the length of the jib, you might increase the height. In certain circumstances, you might reduce the height. Then we have the whole process of dismantling, which is not always the reverse of erection, because the building, the structure itself will have changed, and that may apply different constraints. Communication, absolutely vital, because as I'm sure you all know, if you look at any sort of incident, then very often poor or ineffective communication is at the heart of this. And then very importantly, change management, because if things change, as they often do, and the changes aren't communicated, then that can be a recipe for disaster. We've put quite a lot of effort into producing a very comprehensive RACI chart. This is indicating for each activity, and this is only part of it that I'm showing you now, we have a matrix which indicates who is responsible for that particular task, who is accountable, who needs to be consulted, and who just needs to be informed. So you can see here right at the top, crane selection, the client may be consulted, the principal contractor will be both responsible and accountable, the designer needs to be informed, the base designer needs to be informed, and the crane supplier needs to be consulted. So this is a way of trying to make sure that everybody is aware of their role within the various tasks to be carried out. And then the final chapter before one gets to the appendices is foundation and tie inspections. So we're talking about the pre-erection inspection, so that you make sure that the base or the tie sites and so on are ready to put the crane up. Then after the crane has been erected, you have an initial thorough examination just to make sure that the whole system has the required integrity. And then we go to regular foundation monitoring. It's the frequency, the records. We look at deformation of the foundations. Have they moved at all? Daily checks, weekly inspections, and then there is a bit of advice on the thorough examination of tower cranes. So the point here is that you can't just put the crane up and expect it to carry on without any sort of monitoring. Very important that the foundations are monitored to make sure that they are performing as they are expected to. And here is a pre-erection inspection checklist, which is gives basically some pointers on what to look for. And here we have a foundation pre-erection inspection report, which again can be used to record the findings of the inspection. And here's a little checklist which highlights the checks required during the monitoring during the life of the foundation on site. Now moving to the appendices, Appendix 1 lists the different types, shows the different types of tower crane and their various features. And we start off with a basic top slew. These are the larger tower cranes, and then the slewing tower. These are the smaller self-erecting tower cranes. And then we go through the various types that are available and their benefits and disbenefits. Appendix 2 talks about loading of structural elements, the various types that there are, types of ties, types of cast-in foundations, the importance of getting cast-in foundations set at exactly the right height, not too low and not too high. The point of this little diagram of a bolt here is the business of making sure that you have enough grip length in ratio to the diameter to ensure that when torque controlled bolts are done up, that if there is any settlement, you don't end up losing the preload in the bolt, which would make it far more susceptible to fatigue. And Appendix 5, which is loads on tower cranes. There are obviously the structural loads. There is wind loading, which is very important. And we give some advice on how to determine the wind loads on cranes. You have to bear in mind the effects of nearby buildings, which can lead to funneling and increase in wind speed locally. If you have a particular issue with wind speed in the wind region that the site's located in, it may well be worth carrying out a site-specific survey so that you can determine whether the topography and location of the particular site allows a lower reference wind speed, which obviously will have a significant effect on foundation and tie loadings. Manufacturers will normally provide the in-service loading, the out-of-service loading, and probably the erection loading, because depending on the configuration of the crane, the type of the crane, any one of these may be the highest loading. And so you need to consider all the different types of loads when you are deciding which are the limiting values for design. Ice and snow loading is not normally considered by tower crane manufacturers unless the crane is going to be used in alpine regions, and in that case the purchaser generally asks for specific information. So in the UK we don't normally take account of that. And finally, I would like to give an example of what happens if it all goes wrong. This is a tower crane that fell over in Seattle back in 2006, and as you can see, it's knocked off the corner of an apartment block, and sadly a lawyer who worked for Microsoft ended up being killed by this. there was an official inquiry, and it basically blamed the inadequate design of the foundation. What they found was that the loads that were actually in the steel H-frame structure were considerably higher than the design had allowed for. And the result of that was fatigue failure, and there'd also been a lack of maintenance and particularly inspection, because obviously with fatigue cracks, generally they grow at a particular rate rather than leading to instantaneous failure. So if you have decent inspection, there is always the possibility that you will be able to catch the fatigue cracks before they lead to total failure of the structure. So basically the four issues that there were here were poor planning, inadequate design, lack of maintenance, and lack of thorough examination or inspection. So that's just a very, very brief example of, and then unfortunately there are many more, of where if you get it wrong with base design, then inevitably the crane is going to fall over. And if the crane collapses, then inevitably people are going to get hurt and sadly maybe even killed. Right, well, thank you very much for listening to that presentation. As Will's already said, if you've got any questions, if you could just pop them into the question box, that would be great. And what I would like to do now is to hand over to Stuart, who will be talking in some detail about the worked examples. Thank you all very much.
Thanks, Tim. I'm Stuart. I've just made you the presenter of the webinar. Great. Thanks.
Okay, so the guide contains a lot of details of foundations, explores them in a great deal of detail because they were challenging to design, because the Eurocodes are a fairly complex set of codes, and applying them to situations for which they were not specifically designed was interesting. Now this all came about because maybe 6 years ago now, I was designing a tower crane base, and it had just been issued, and a new load case came out which was wind on the front of the tower crane, and it was 25% higher than I designed the base for. So I thought, well, why is this? I've been designing tower crane bases now for 25 or 30 years. I've never had this before. I had to revise the design of my tower crane base, make it all heavier by 25%, and wondered why. So I foolishly stuck my head above the parapet and said, why is this? And got involved in this new guide for tower cranes. And we have now taken account of the different load cases which you might get from a manufacturer. So this is typically what you will get from LEPA. You don't always get the same information from every tower crane manufacturer. So here they're giving you 4 load cases: crane in operation, which we're all used to. The crane out of operation is now divided into 2: storm from the rear and storm from the front. And then, as Tim was mentioning earlier, you will often get the erection case, which can be the worst case for certain cranes. In this particular case, you can see that storm from the front is the worst case. This load case came about because there were some examples of cranes which had suffered from wind loading to the front and had failed as a result. This condition can occur if a crane is adjacent to a very tall building, and the buffeting effect of the wake can send the crane spinning round, which means it gets wind on the front. And of course, sometimes if the crane is locked, you will also get the situation of wind on the front of the crane, but that is something you specifically need to refer to the tower crane manufacturer if you're in that situation and can't allow free out of operation wind sail effect, so the jib points downwind. So looking at the various codes which we've had to deal with, we have BSE in 1990, which is the loading guidance for general civil and civil engineering structures. But there's also a specific tower crane code, which is 13,001. Now, unfortunately, they're not compatible. So those of you like myself who are structural engineers will be familiar with the typical load factors of 1.35 on dead load and 1.5 on live load in the Eurocodes, down from the old 1.4 and 1.6. However, in 13,001 deals with a number of different situations for tower cranes, and the load factors vary from 1.1 up to 1.5. So the first challenge was to try and reconcile those issues, and the FEM, which are the European Materials Handling Group, which includes the tower crane manufacturers, produced some guidelines which were helpful in untangling these load factors. And we have basically adopted those guidelines rather than the basic Eurocode load factors. And this in fact results in different load factors for the storm on the front load case, which is an unusual load case, almost an accidental load case, and the other general load cases. It is therefore within the spirit of the Eurocodes, whose aim is to get a consistent factor of safety. The Eurocodes aim for consistent reliability, which is in essence another way of saying factor of safety. It's basically a statistical concept, and it's a way of measuring how reliable a structure is in terms of its likelihood of failing. Now they relate this reliability to the consequences of failure. This does occur in the British standards to some extent. If you look at agricultural buildings, they will generally have lower load factors or factors of safety built in than ordinary residential or commercial buildings. So in the Eurocodes, they define 3 consequence classes. CC3, there's a high consequence of loss of life, or there are great economic consequences, and they give examples there of grandstands and public buildings. Medium is what most items fall into, so there's a medium loss of life and considerable economic consequences. And there they put residential and office buildings, public buildings, etc. And then you have low consequences, which again are typically agricultural buildings. So based on those consequences of failure, they then define reliability classes or reliability indices, 1, 2, and 3. 3 being the most reliable and 1 being the least reliable. And they derive a beta factor, which is a statistical concept which is quite complex and we don't actually have to go into. In essence, varying the load factors is one way to vary the reliability of a structure. So the target of the Eurocodes is to define to achieve a defined level of reliability. Now we have another statistical feature, which is wind, which is a statistical factor. Those of you who are as old as I am may remember CP3 Chapter 5 Part 2, which gave you a nice little chart of the statistical factor with different probability levels for different periods and years. If you take the typical 50-year return period, the statistical factor of 1 gave you a probability level 0.63. And in those ancient days, we used to design temporary works based on having a same probability level over 50 years for the temporary works which existed for 2 years, which gave you a reduction factor of 0.77. We no longer do that, even in general. There are some items of temporary works which do attract a reduction factor in wind loading, such as hoardings, You may refer to the Temporary Works Forum's design on the design of hoardings and some scaffold structures. It's still not as low as 0.77, but there is a reduction factor. However, a tower crane is categorized as consequence class 2 and therefore does not attract a typical reduction in wind loading. However, there is a complication in that tower crane wind loads are defined over 25 years, not 50 years. So where does this lead us? It leads us to a set of partial load factors, which are different for in-service and out-of-service. And the FEM defined two sets, one if second-order dynamic effects are included by the crane manufacturer, and one if they are not included by the crane manufacturer. So if in doubt, use the higher set. Otherwise, you need to go back to the manufacturer and ask if he's included second order and dynamic effects in the loads that he has given you. You can see that they vary quite a lot from 1.0, well no, that's for a load which is resisting your overturning moments, as opposed to a load which is contributing to them, which has a positive factor of 1.5 or 1.35. There was a further complication in that the FEM figures do not take account of the Eurocodes 7 combinations for loading on the ground. Now, for those of you who are not familiar with Eurocode 7, Eurocode 7 defines two load combinations, a structural combination and a geo combination. And they're generally referred to as combinations 1 and combination 2. So combination 1 is a normal EC load factor of 1.35 and 1.5 with a material factor of 1. Combination 2, they have varied the material factor on the ground, giving a combination 2 load factor of 1 dead and 1.3 live, with material factors on the ground of 1.4 on the shear strength and 1.25 on the friction strength. So we had the challenge of combining that with the FEM data to get a set of figures to which we could work. After a lot of consultation, we came up with some factors which are in the guide for combination 1 and combination 2 loadings. Again, you can see that the storm from the front load case, which is in the middle there, goes down to 1.06 as a minimum, whereas the maximum crane operation load factor is up at 1.5, so there's a considerable difference between the two. You are always, of course, at liberty to take the higher load factor that will give you a less economic design. So we've gone extensively into the examples. I would say it occupies about 50% of the guide. There's something like 100 pages of them. I'm hoping we've looked at all the different types, certainly all the common types. So we've looked at a typical cruciform on unreinforced pad footings, a reinforced square gravity base in sand, a reinforced square gravity base on a stiff clay, a pile square base, reinforced concrete beams for a rail mounted crane, a steel grillage on a building core, and plunge column foundations to a cruciform base. Now, as far as I'm aware, there is no other published data on the design of plunge columns, so that in itself is useful and took a lot of research. We actually went back to the original data produced by one of the major piling manufacturers who did some tests on plunge columns quite a long time ago now. So those are the 6 examples we've looked at. Obviously, the principles can be applied to any other example. So we've done square ones, which are the simplest, but the principles will also apply to rectangular ones. And a piled square base can be extended to other shapes. So these are the types we're talking about. Just some fast forward. Here is a cruciform pad, cruciform based on unreinforced pads. On the left there, you can see there's a base put down on the pads. In the old days, we didn't fix those down. They just sat there by friction. However, it was found that these did slowly walk off their supporting pads, because in fact, under certain conditions, there is no load between the beam and the pad. And with the torque added onto it, it could move along slowly. So the recommendation now is that these are always restrained against lateral movement. You can see in the bottom right-hand corner picture, there are some restraints to that grillage there. The restraints should allow vertical movement because the grillage is not designed for being held down at that particular location, unless the manufacturer has been consulted and that is the design case. Normally the cartilage on the crane is sufficient to hold it down. Here's a reinforced gravity base in sand and or clay. This one, as you can see, was combined with a column foundation. Not an unusual situation in a busy city centre site. This is a pile base. You note the legs here are clear of the piles, which is a key thing to remember if you're designing a piled base. Otherwise, you'll find these plates get in the way of the pile reinforcement. And the pile reinforcement needs to have a full tension anchorage into the base because they're tension piles as well as compression piles. Rail mounted tower crane. This is basically two strips of concrete, so the design is in principle similar to a gravity base. So grillage stuck on top of the core. You can see here the stiffeners around the two main beams, tie rods going down, anchored down within the core. All the necessary checks on the core walls are included in the example. And a grillage on top of some plunged columns. These look fairly slender and they're filled with concrete for some additional resistance. That was all that could be fitted in there by the space and the rig that was available on site. Now the examples contain extensive code references. If you need to design a beam in bending, then you should find the necessary code references within this guide. You need to design some reinforcement in bending, ditto. So wherever the code is used, the reference is on the left-hand side, and there's other guidance referred to on the left-hand side as well. And the formula obviously written down in the guide. These are very extensive, as you can see here. So we've got BS 1025. This arises because when you're dealing with steelwork to the Eurocodes, if you want the allowable stress in the steel, the Eurocode refers you to the national annex. National annex then refers you to the product standard. It took me a long time to work my way through this, but it's all shortcut for you here. If you want a bit of steel, you know where it is in that BS there. Other items, the Steel Code 1993, Part 1 is the general section. For shear buckling, it's in Part 5, Part 1, Part 5, and for connections, it's in 1993, Part 1, Part 8. Excuse me. So all the references are here, and I commend those to you. We did find one surprising fact. For a pad gravity base, the most critical failure isn't at 45 degrees, which I'd always assumed or worked on before. It is actually at a slight inclination to 45 degrees, probably about 40 rather than 45 degrees. And that occurs because the capacity of a rectangular bearing area is less than that of a square bearing area. So despite the fact that the area is slightly larger, its capacity is less, and the net result is less than a square base. We don't have enough experience yet to see how much of an issue that is, but from what I've done, it seems to be 5 to 7%. In terms of will we ever get rid of Eurocodes, I think the answer is no. So BSI has secured membership of CEN and CENELEC, the pan-European code writing organisations, and they plan to continue that relationship and to continue the use of Eurocodes. Having had some experience using them, I think that the next set will hopefully be simplified, but I can't see anyone starting from scratch and rewriting our codes. It would be too much of a job. Thank you for that. Any questions, just note them down. I will hand over to James to talk about some issues on the site.
Thanks, Stuart. James, I'm just going to hand over control of the webinar to you now.
Hi, my name's James McFarlane. I'm a chartered structural engineer with Langer Wilks Temporary Works Design. This presentation is going to have a look at craneage with a particular focus on high-rise craneage, particular focus on Langer Wilks projects, and a particular focus on the temporary works involved in erecting and operating cranes, i.e. bases and ties. It'll be a slightly shorter version, this presentation, than the live webinar, but hopefully a reasonable amount of the content will still be there and all the important points shouldn't be lost. This photo is about a year and a half old. It's Canary Wharf, just east of central London. The building with the cranes under construction on the left-hand side of the picture is Newfoundland, which is a 60-story or so residential development, which is now nearing completion. This photo again is about a year or 18 months old, giving an idea about the construction methodology. You can see the jump formats of the core, you can see the screens, you can see the cladding start, which must be complete over about 20 stories at the stage this photo was taken. The opponent works structural designers were WSP, and they would have had a number of challenges, which also applies to temporary works design. One challenge being the location, meaning that potential channeling of wind down the dock between the existing buildings, hitting Newfoundland that you can see under construction in the gap between the buildings in the centre of the photo, hitting Newfoundland flat on its, it's not particularly deep as a structure in the direction that this photo is taken, east-west. So there's potential for additional wind loading due to the proximity and the arrangement of neighbouring buildings. There's also a tube line running directly below the basement, so further challenges in terms of temporary works design. The cranes at Newfoundland are external cranes outside the building footprint and tied to the edges of the slabs. There are a few more options that tend to be less widely used. The type of cranes used in Newfoundland are common, and they're termed bracketed under external cranes. Another option is for a high-rise development is to support the crane directly on the core, either on the permanent concrete works of the core or on the temporary formwork, the jump form rig or the slip form rig of the core. Either of these two sub-options for a core mounted crane is unusual remember, these are also cranes that would climb with the core as it climbs, as it's built level by level in advance of the floors, the external floor plates below. These diagrams are taken from CIRIA guides, relevant to this presentation, gives an idea about how structurally it works. It's similar in terms of support arrangements to a placing boom, but the loads would be much greater for a heavy crane than for a typical placing boom. It works in a similar way in terms of the vertical loads from the mast taken on the permanent concrete slabs. Typically, there'll almost certainly be quite a few levels of backpropping. The moment, due to the mast and the offset horizontally, say, of the load that's been lifted, will result in push-pull horizontal forces that again are taken by the concrete propping slabs. The Shard, for example, was built using a core mounted crane, but my understanding is at that time, when the Shard was under construction, it was the only crane of its type in this country. Langerock's subsidiary company, Select, do, I think, have a crane that's capable of being mounted on a core, but again, it's not particularly frequently used. In terms of other options, building a high-rise with minimal external heavy temporary works is an option. 80 years ago, the Empire State Building was built. It was built extremely quickly, 100 stories in about 6 months. And as you can see from this photo, there wasn't much in terms of heavy craneage. The derrick cranes that you can see on this photo at the top look pretty skinny. They did have elevators, hoists inside the building for transporting materials from ground floor level. But as I said, nothing obvious in terms of a high capacity, heavy craneage. And there's another option which is used typically maybe in medium rise construction, sometimes also in high rise construction, is mounting a crane on a core, but a core that's finished, that's reached its peak. And that's what you can see in this photo. This is a Langerock project finished about 6 months ago, an office building near Paddington in central London. On the left-hand side, you can see a crane with only a short stub mast. You can see concrete blocks, like Kentledge, helping reduce the tension loads at the supports of that crane. And it is sitting on a concrete permanent works core. And the crane was only installed in that location when the core had been completed. In the middle of the picture, you can see a typical example of an external crane. So going back to the type used at Newfoundland, the common type, it's only a 20-story building, so the crane only needed one level of ties that you can see at the top of the building. But that's an example of a more common type. This is the same job, and this is the core mounted crane. You can see about 14 blocks of Kentledge. You can see in white below the tower crane mast a deep steel cruciform base. That's an off-the-shelf product that is available for reuse for supporting the crane and for supporting the Kentledge. Below that in grey, there is a gridage, a bespoke gridage to transfer the loads from the cruciform base into the concrete permanent works. And that's what you can see here. The bolt details and the supports are fairly, you don't need huge numbers of bolts or huge diameter bolts because you've got the Kentledge, the concrete blocks. The support reactions are high compression, but very little, if any, tension. So the bolts don't have to work as hard as would be the case if you didn't have the Kentledge. Checking for the deflection of these beams is key, because if the grey gridage beams start deflecting, that will cause the crane to lean. So the calcs are run through, finite element models prepared, and the potential worst case lean verticality tolerance of the crane is checked and deemed to be acceptable or not. If it's not acceptable, the gridage will need to be increased in size. In terms of the bases for high-rise crane, this is potentially a base used for a high-rise crane, but it's also a typical anchor detail that might be cast in from a base for a low-rise job requiring, say, a 50-meter high crane with no cranes. So the point really is that base a high-rise crane could easily be fairly similar to the for a low-rise tied crane. If the crane goes from 50 meters to, say, 200 meters, then yes, you'll need a series of ties, maybe every 20 or 30 meters in terms of vertical intervals between ties. But in terms of loads on the base, the vertical loads will start to creep up slightly, probably, if you go from 50 meters to, say, 100 meters with some ties. But the moment on the base, if anything, might reduce. So the bases for high-rise cranes tend to be very similar to the bases for low-rise cranes. That is a recent Langerock project, student accommodation about 40 stories high, again in West London, a bit further out from Paddington. Use of bridging columns on that project. Back in Newfoundland, and what these slides are moving on towards are looking at ties and the various options for how ties can be achieved. So I mentioned sort of 20 or 30 meters in terms of vertical intervals. And Newfoundland, there were thrust blocks attached to slabs to which the ties were attached. Here you're getting a little bit closer to the building. Still quite an early stage of construction, but a number of ties already in place. Tends to be 3 arms off the collar around the mast to which the ties need to be attached to thrust blocks. And that's an example of a thrust block. Heavy, bespoke plate girder eye sections, preloaded macalloy bars or similar through the depth of the concrete slab, pinning the temporary steel grillage to the slab, and the horizontal load at the base of the steel grillage is taken into the concrete by friction. That's the interface between the grillage and the ties. Here, in this photo, we're waiting for the ties to arrive to attach the thrust block to the mast so that the ties can do its job and restrain the tower crane mast. There's similar details at Norfolk Road. Again, heavy eye section views, stiffeners, bolts into the concrete slab, preloaded to set the values. Extrusion zones and slab, gas pops below the slab. The thrust blocks weigh a reasonable amount in terms of their self-weight, and so just to give the slab a bit of a helping hand in terms of minimising any possible risk of cracking, etc., a bit of deflection, it makes sense to have exclusion zones, to have gas props, backpropping, especially as not only have you got the self-weight of the thrust block, you've also got the vertical reactions due to the horizontal load being applied from the ties to the thrust block. The other option, as I said, is a bridging column. The other obvious option, so I haven't actually, as part of this slightly reduced size presentation, got a photo of a bridging column, but they're quite common. I mean, this obviously is a photo of showing 2 concrete slabs of a building. A bridging column would be much heavier than a gas leg, which is what you can see here, typically sort of 300 square hollow steel sections. But the idea is that the tie is attached preferably around midspan of a temporary steel bridging column, a hollow section, which then would be bolted to the slab above and bolted to the slab below. The obvious advantage compared to a thrust block is you're transferring the loads from the tie into 2 slabs as opposed to 1. The final slide is a recent project. This photo is about 3 months old, and although it's not really a Langerock job, some of the cranes for this project are supplied by Select, the Langerock subsidiary. Here you can see a single tower crane which has got quite long ties back to a core. My understanding is that these are slipform cores, and these will be, when finished, the world's highest modular buildings. The idea of this type of construction is to build a core quickly with a slipform and then attach modular units to the sides of the core to make up the completed building. So at this stage of construction, the cores look completed. You can just see on top of both cores a little stub mast, and about a couple of months ago, 2 cranes, 1 crane on each core, was then installed. Those would be core mounted cranes, static cranes, because the core's finished, to take over from the external tied crane in order for the modular units to be installed. In terms of the offset, looking at this photo, a few things to consider. One is the offset of the tower crane mast to the core, which is quite considerable, which could lead to higher reactions at the supports of the ties in the concrete pernal works than would be the case if it was possible to get the mast of the crane a little bit closer to the core. When you're dealing with very slender structure, dynamics starts to come into play. And if you've got a slender concrete core and next to attached to a steel crane, then a consideration potentially would be natural frequency of the core compared to the natural frequency of the crane, checking for possible resonance. And the other thing is, because you've got 2 buildings next to each other, another potential design check would be interaction between the 2 cores in terms of wind loading, potential channeling of wind load from one core onto another, meaning that potentially the overall wind load on one core might be higher given the proximity of another core than would be the case if it was just one single standalone core. So an impressive project under construction, as I said, at the moment. And if you're ever passing through Croydon, I'd recommend keeping an eye out for it. That concludes my presentation. Thank you for listening.
Okay, thanks, James. I'm just going to take control of the webinar for just briefly. On to the Q&A. I'm going to give people just a couple of minutes to type any questions that you may have for today's presenters into the question box. So I'll give you 1 or 2 minutes to do that. And then if we have some questions, we'll go through them. If we don't, I'll close down the webinar. But please type your questions now into the question box. Thanks. Okay, just a couple of questions on whether the webinar is being recorded and will be available to anybody tuning in today. The webinar has been recorded, and we might see if we can do something with James's to improve the audio. But that recording will be available fairly soon, and we'll email people when that's available. Other than that, I don't see any other questions from delegates. Of course, if you do have a question that you think of afterwards, I'm sure that we'll be available. We can circulate that to the speakers today. Just a reminder that the C761 tower crane base and tie design is available from the CIRIA bookshop. And I will say thank you very much to Tim, to Stuart and to James for their presentations today. And I will close down the webinar there. Thank you very much.